Alright, this is the last day for our lecture on integration by substitution. I just have a couple problems to talk about. The first one, what we're going to do is we're going to find this indefinite integral in two ways. So, how are we going to do that? Well, I'm going to go ahead and just flip my page here. So, I'm going to evaluate this first by choosing my u to be cosine of x. And then I'm going to evaluate the same integral, but I'm going to pick my u to be sine of x. So let's go and do the first way. If I choose my u to be cosine of x, I now have my du being negative sine x dx. What I would want to replace this as is just u. That would take care of this portion. I need sine x dx, so I'll move my negative over. And that way I'd have sine x dx by itself. So I'll put a negative out front with a du. So I'm getting negative u squared over 2 plus c. So that means that this solution would be negative 1/2. We'd have cosine squared x plus c. Now, this other one, when we solve for it, we'd have du equals cosine of x dx. Therefore, when we solve this, we'd have u, and then I need just a du. So we end up getting u squared over 2 plus c. And this gives me 1/2 sine squared x plus c. Now, you might be asking how these are the same. But using some different trig identities and such, we can show that they are the same. Just understand that you could evaluate this in two different ways, that both of them would be correct. The next part we want to talk about is integration of even and odd functions. So if we know that something's an even function, what we know is that it's symmetric about the y-axis. Symmetric about y-axis. What that means is that the coordinates x, y and the coordinates x comma negative y are both on the graph. If we know it's an odd function, then we know it's symmetric about, and I just did that backwards, the more I was thinking about it, symmetric about the y would have something like this. So we'd have x, y, and it'd be negative xy. Sorry about that. Let's correct that. So I'll just erase the whole thing right here. Negative xy. The other one was symmetric about the x-axis. So symmetric about the origin. What that means is that the coordinates x comma y and the coordinates negative x comma negative y are both on the graph. If we know it's an even function, we can just double the area from 0 to whatever number we're talking about. If we know it's an odd function, then what we can do is say that the area is actually equal to 0. So I want to show you an example of this. This one we're going to evaluate this integral using the property of even and odd functions as an aid. Now we could go ahead and just evaluate this in old-fashioned way, but we're going to go ahead and show you how you can use odd functions to know what the integral is without actually computing it. So what I'm going to do is I'm going to take this function, and since I know that x, y, and negative x, negative y would be on a function that's odd, meaning symmetric about the origin, I'm going to go ahead and plug in negative x to see if I get a negative y, meaning, let me rewrite it this way in all honesty. We'd have y equals x times x squared plus 1 cubed. So what I want to know is if it actually equals the negative part. So I'll put a negative in for all my x's, a negative x in for all my x's, and I'll simplify this, and I get negative x, and I get x squared plus 1 cubed. So what I actually ended up with was the negative y portion of it, so it was negative on both sides. So I know it's symmetric about the origin. Since it's an odd function, we now can say that from negative 2 to 2 of f of x dx, we know that the area underneath the curve is 0. And we're finished. We don't need to take this any further.